In this third lecture, we shall consider the self and mutual inductances. Consider a closed loop, a closed conductor, which carries a current I. So, this conductor will produce, this current will produce a magnetic field in its neighborhood, and some flux will also be linked with it. So the flux linked with it will be proportional to the current flowing through the circuit. So we call the flux linked with the circuit is proportional to the current I, because the magnetic field that is produced is proportional to I. If we do not consider any ferromagnetic material present, so B is proportional to I, the current circle flowing through the loop. And since the flux linked with it is B times area, if we consider the ring to be a rigid one, that is whose shape does not change with time, then the flux is linked with the magnetic field, that is and we call it this. Where L is the constant of proportionality, we call it the coefficient of self-inductance, or simply the self-inductance. If I depends on time, then we write the EMF induced is so this is minus L di dt. This minus sign, this is called back EMF, because it is in the opposition of the EMF applied by the battery or any other external sources. So this is called the self-inductance. That is to say, we talk about self-inductance when we try to measure the flux linked with the circuit due to the field produced by itself. This expression we can define from this expression self-inductance L to be numerically equal to the flux linked with it for unit current, and from this you can define self-inductance as the back EMF generated within the circuit when the current in it is changed at a rate of 1 ampere per second. The practical unit of L is Henry. These are available in text. We shall now consider the application of self-inductance in few simple cases. As the first case, we consider a solenoid. If we consider a solenoid, infinite solenoid, or very long solenoid, very for very long solenoid, magnetic field is mu0 Ni, where N is the number of turns per unit length. So this is mu0 N by L. L is the length and I is the current. So if we have a solenoid of this form, this is the axis of the solenoid. If A is the radius, then area cross-sectional area is pi a square. So this is the area, so flux linked with this for each turn is this multiplied by A. Since there are n turns, so total flux linked with it is NAB. So this is equal to mu0 N square A L times I, which gives you the L is equal to phi by I is equal to mu0 N square A upon L. We see that the self-inductance may be increased by increasing A by N, the number of turns. As the number of turns increases, the self-inductance increases quadratically. By increasing A, we can also increase self-inductance, but you must be careful that as the A becomes A, the radius of the cylinder of which is the on which the wire is being wrapped to form the solenoid, is A becomes comparable to L, the field falls off as we go away from this. So there is a precaution to be taken. Here we have considered the B to be uniform over the cross section. Now, if we have a solenoid, for a general solenoid, consider a solenoid. For a general solenoid, here the field is given by I'm explaining the terms. Here we have considered a solenoid of length L. This is A, radius of the solenoid is A. This is the L, and this is along Z axis. And we have considered the field at a point P, which is at a distance Z from one end. So this much is L minus Z. This is the expression for the field. If we consider such a cylinder whose length along Z axis is dz, so number of turns, if we call N is the number of turns per unit length, so L is the number of turns per unit length, then the number of turns within this is N dz time cross sectional area times B is the flux, and to get the total flux we must integrate it over Z from 0 to L. So the flux linked with it is B N dz A, and this is being integrated from this 0 to L. So for this we write capital N by L. So this much is mu 0 N square L by 2L square A, and the rest of the thing is 0 to L. It is easy to say show that both the terms have equal contribution, that is this and this part have equal contribution, so we evaluate this part only. Z dz A square plus Z square to the power half integrated from 0 to L. So this is U du, where U square is A square plus Z square by U. and this term is also there. So the phi is I must write it over here. This is equal to, this part will go mu 0 n square a I by L square times a square L square square root minus a. If we consider a long solenoid, that is, we may write this and another L is taken within this. If we divide it by I, we will get the expression for L. So for a general solenoid, this is the expression for phi. So L is given as phi by I is equal to mu 0 n square a by L square which for a very long solenoid, in the approximation when a by L tends to 0 or when L is much greater than A, the expression becomes this, and we can neglect the, so this becomes mu 0 n square A upon L, the same expression. Now we consider a coaxial cable. As the second example, we consider a coaxial cable. As we have considered earlier, the coaxial cable consists of two concentric hollow cylinders. Two concentric hollow cylinder, the inner one, and coaxial hollow cylinder. The inner one has a radius A and the outer one has a radius B. So that this much is A and this much is B. If I current flows up along the inner wire, then the same current I flows down the outer cylinder, so that B is 0 outside and the B is 0 inside, and B persists only in between the range A to B. If we consider it to be the z-axis, then the field is governed by for rho between B and A. If we apply Ampere's circuital law and we consider the Amperian path to be a circle of radius rho whose center lies on the z-axis and the plane is perpendicular to the z-axis, then the field will be 2 pi rho B is equal to mu 0 I, where I is the current in the inner cylinder, which immediately gives you B as mu 0 I upon 2 pi rho. Now coming to the flux linked with it, we consider a cross section. So note that B is along phi cap. we we consider a cross sectional area on the phi is equal to constant surface in the cylindrical coordinate system. So this is ds. ds is equal to d rho dz phi cap. So the flux linked with it, flux linked to is b dot ds and the integration. So writing explicitly, this is mu 0 I upon 2 pi integration over dz, so 0 to L, and this is d rho upon rho from A to B. So mu 0 I L upon 2 pi log B by A. So the self-inductance of the coaxial cable is mu 0 L upon 2 pi log B by A. If we consider the coaxial cable of unit length, then L disappears. Another example we consider for the calculation of self-inductance is the two parallel wires, two long parallel wires carrying the current in the same direction. This is going to be our third example. Two long parallel wires carrying current. So we have one wire like this. This is its axis, and this is the thickness of the wire, cylindrical wire. There is another similar wire. This is the wire axis of the second wire. It is identical, and the axis to axis distance is L. Let me write something L other than L. So this is the distance S. So if we consider a point here which is at a distance rho from the first wire, this is wire 1 and this is the wire 2. So both of them carrying current in the same direction. So field is additive in between this range. So B is mu 0 I upon 2 pi 1 by rho plus 1 upon this much is S minus rho. This is the field. And if we consider a cross-sectional area this much, this is d rho dz, d rho dz, this much is dz, this is d rho dz. The flux linked with it is flux linked with it phi is equal to integration b ds, which now becomes mu 0 I upon 2 pi integration 1 upon rho plus S minus rho d rho dz. The z integration is and this integration extends from here, that is a to S minus d. So it is a to S minus d. So this is first time is mu 0 I L upon 2 pi this part. This integration is log, so log with upper limit s minus d by s minus a, this is not d, s minus a by a, the lower limit a, and this part is also same, so we just multiply it by 2. So the flux linked with it is mu 0 L I by pi s minus a by a, and the L is phi by L, pi by I is equal to mu 0 L by pi is the fourth example. We consider a toroid, and this is the last example of for the calculation of self-inductance that I am going to consider. A toroid is generally consists of an inner circle and outer circle, and where is being wound over it and the current flows through it. Sometimes it is called an endless solenoid. The inner radius is A and the outer radius is B. This is the toroid. The name of the toroid is given as per its cross-sectional area. If the cross-sectional area is circle, that is, these are circular cross-sectional area, that is, if we take a cylindrical pipe and bend it in the form to form a circle, then that will form a circle toroid of circular cross-section area. If we take a rubber slab whose cross-sectional area is a rectangle and it is bent in the form of a circle, then the toroid is called a toroid of rectangular cross-sectional area. If the cross-sectional area of the rubber band is a rubber tube is square, then we call it a toroid of square cross-sectional area. However, if we consider a field over here, the field inside is 0, that is for rho less than A is 0, for rho greater than B is 0, and the field survives only in between. So for rho less than B, greater than A, applying Ampere circuital law, B is mu 0, number of turns I, 2 pi rho. If we consider the cross-sectional area to be rectangular, then rho varies from, this is the rho variation of rho variation varies from A to B, and we are to integrate, to get the cross phi, we must integrate it over the cross-sectional area. This is the height, so we get mu 0 n I 2 pi h, it comes from height, and then d rho by rho from A to B, and this is the flux linked with each turn. As there are n such turns, this is the flux, and we get it as mu 0 n square I h upon 2 pi log of B by A. If the cross section happens to be square, then a special advantage is obtained, h is equal to B minus A. Then h will be replaced for a rectangular cross section, square cross section, and we can get the phi L by dividing it by I. Another thing happens that when the cross sectional area is circular one, For circular cross-sectional area, if we consider the variation of the field along the length, the calculation becomes tough. So for circular cross, this is for a rectangular cross-sectional area. For circular cross-sectional area, if we consider the circular cross-section of appreciable area, then the field varies across the circle and the calculation becomes very tough. So we consider for for toroid cross-section, we assume B to be constant and we use B to be mu 0 n I by 2 pi r, where r is equal to a plus b by 2. This is the mean field. And if we multiply it, phi is equal to NAB. A number of terms, A is the cross-sectional area, A is equal to simply pi r. This is the cross-sectional area. And we get the corresponding expression for the self-inductance. Now I am going to the mutual inductance. Say, consider two coils, two closed loops. They are situated nearby, so that the mutual inductance. We consider one closed loop C1, another closed loop C2. If a current I1 flows through this, it will produce a magnetic field. The magnetic field is called B1. This flux will cross the surface area 2. So the if a current I1 flows through the conductor 1, which is in the form of a closed loop, then it will produce magnetic field in its neighborhood, and some of the magnetic field crosses the loop 2. So flux will be linked with the 2. So flux linked with 2, flux linked with 2 is given by phi 2, which is proportional to I1, and we call it M21 I1, because the flux linked with it is this. Similarly, if a current I2 flows in the conductor C2 and a flux is linked with 1, and we call it phi 1 is equal to M1 due to 2I2. In terms of the EMF, the result becomes induced EMF is equal to minus d phi 2 dt is equal to we want to go further, that is, what is the phi 2? Phi 2, basically phi 2, the flux linked with this is B1, the field produced by the 1 times ds2 and integrated over the conductor 2. So this is field due to 1, and this is the cross sectional area. We can write it as curl of A1 dot ds2 over conductor 2. You know that this operation is about the field coordinate. So in this expression, the field coordinate is on the conductor 2. That is all across this. Basically, this is nabla is with respect to 2. Coordinate denoted by suffix 2. So the integration and differentiation is on the same basis. So we can use Stokes theorem to write it as C2 dr2. Here we have used Stokes theorem to convert the surface integration into the contour integration. Now what is A1? A1, we know that, let me write first C2, and for A1 we write where that, we have used the notation that with respect to this is dr1, this is dr2, this is r1, this is r2, this is capital R. This is the geometry that we have used. This is the origin. This is I1. Here we have used the expression of A1 as mu 0 I1 upon 4 pi integration over. So the mutual, if we compare it with this expression, we get m21. So what we do, we compare this with this. So m21 is equal to mu 0 upon 4 pi integration over c1 c2 dr1 dr2 by r. You see that R, capital R is the scalar, and R1, the expression is symmetric about R1 R2, so we can call it as M12 also. Nothing changes if we interchange the subscript 1 and 2. So that's why now we can call it as the mutual inductance. So the relation now becomes phi 2 is equal to mi1 and phi 1 is equal to mi2. That is, if current I flows through the coil 1, then the flux linked with the coil 2 is equal to the flux linked with 1 when the same current I flows through the coil 2. That's why M is called mutual coefficient of mutual inductance, or simply the mutual inductance. This formula is known as Neumann formula, as per Dutch physicist von Neumann. And the fact that M12 and M21 are the same, this is known as the reciprocity theorem. Now we shall calculate mutual inductance in few simple cases. Firstly, we consider a standard solenoid. A standard solenoid that we generally use in laboratory consists of two solenoids. One is a very long one called the primary, and a short one which is known as the secondary. So standard solenoid comprising of primary and secondary. This is not a single solenoid but a combination of two solenoids. This is the primary, and here we have the secondary one. This is the primary one, primary through which the current flows, and this is secondary. The flux across this is generally used. Now everything with respect to the primary is denoted by the subscript P, and everything with respect to the secondary is denoted by the subscript S. So the field produced by the primary, we assume the solenoid primary to be very long. So this is mu 0 air core mu 0 NPIP, where this is the number of turns per unit length. If we can write it as mu 0 NP, total number of turns, LP, length of the solenoid LP, times IP. Now the flux linked with the secondary is number of turns of secondary, cross sectional area of the secondary, times the field in which it is placed. So this is mu 0 NP NS alpha S IP by LP. So the mutual inductance for this pair is this is the coefficient of mutual inductance between the primary and secondary. As the second example, we consider two circular waves of parallel cross-sectional area of parallel cross-section, and they are separated by a distance. So we have one circular area and another circular area. This is A, this is B, their separation is Z, and so the field, if we consider this is 1 and this is 2, current 1 I1 is flowing through it, so the field produced by this over here, this is the B produced by it, is mu 0 N1 A square by 2 A square plus Z square to the power 3 by 2. So we consider the field at an axial point due to a circular current carrying conductor. The field is along this direction. This is the direction of B, so it is scattered. So the flux linked with this is the secondary, the flux linked with it, number of turns in it, its area pi B square times B1. If we write everything, the mu 0 N1 N2 pi A square B square, or I1 is missing there, I1 by 2 A square Z square to the power 3 by 2. So the mutual inductance M is equal to phi 2 by phi 1, phi 2 by I1. This is mu 0 pi n1 n2 s square b square upon 2 s square plus z square to the power 3/2. Now that's the third example. We consider two circular cross sections. One is fixed, it is the one coil primary, it is its end cap, the normal area, and there is another concentric circle. This is 2, this is having n2 cap. So we have to calculate the field at the, so B1 in this case, B1 is the field due to the coil 1 mu 0 n1. This is s square I1 by 2a cube because z is equal to 0. So this is mu 0 n1 I1 by 2a. This is the field, and the field is along n1 cap. The field, if we write it in the vector form, so B1 is equal to mu 0 n1 I1 by 2a along n1 cap. The flux linked with these two is equal to the cross sectional area of 2, that is A2 N2 N2 cap times B1. So this is mu 0 n1 n2 a2 by 2a n1 dot n2. So if we have used this angle, this is the angle between them. Oh, I1 is missing. I1 is missing. So M is equal to phi 2 by I1 is equal to mu 0 n1 a2 n1 n2 a2 by 2a times n1 dot n2, and this is equal to mu 0 n1 n2 a2 cos of theta. There is an experiment included in your syllabus which is for the calculation of mutual inductance between two pair of coils having the common center, concentric, and one the primary, one is called primary through which a current flows, and it is a fixed coil, and the second coil can be rotated so that the axis, the center remains the same, but the angle between the two coils may change from 0 to 180, and you are to calculate the of M. As is evident from this, the variation of M is mod cos theta, that is for this case mutual inductances. If we consider the variation of mutual inductance, this is the angle of theta and this is M. This is simply the mod cos theta plot.